Lesson 60 is on circle proofs, and so we'll be doing triangle proofs using triangle congruency postulates to do these proofs, but we'll be adding some of the rules about circles. And you have a new rule in the beginning of Lesson 60, the perpendicular bisector of a chord theorem. So study that rule. This lesson is based off of lessons 9 and 10, where there's lots of rules as well about triangles and circles. So you might want to take a few minutes to go back and memorize those, study those. The more axioms, postulates, rules, and definitions you have memorized, the easier it will be for you to complete proofs. Now, one thing we also talked about in Lesson 59 was that because of their almost exclusive use of the compass and the straight edge, the Greeks' labors in geometry that directed them to make many connections between circles and triangles, making the invisible visible between those two things. And in Lesson 60, what we're going to do here is use circle properties to draw triangles and prove congruency between pairs of angles or sides. And two circle properties we'll use a lot are the circle definition, that's in Lesson 9, the tangent segments theorem, that's actually in Lesson 11. So look at that lesson as well, plus the perpendicular bisector of a chord theorem, that's at the beginning of this lesson. So that theorem is based off of Euclid's proposition 1, not the equilateral triangle proposition that you've covered already, but this one's from book 3. The proposition 1 that you're familiar with, or maybe you've forgotten it, but hopefully you'll recall that you've done that proposition 1. That is from Euclid's book 1. So let's just go ahead and get started with this. We're just going to do a couple of proofs here. Example 60.1, given circle A and that AE is perpendicular to that segment CD, prove that CE is congruent to DE, and we can use the hypotenuse leg theorem in the proof. We don't have to. There's other ways we could prove this, but that's what this problem is directing us to do, is use the hypotenuse leg theorem in the proof. So remember, we talked about that before, is that a lot of times on a proof there's more than one way to prove something. So one of the first things we do is to mark off our given information, just like in Lesson 58, what you learned there. And let's just go ahead and do that. We already see that there's a right angle mark there between AE and CD, but we've also been told to use the hypotenuse leg theorem in the proof. So we should start thinking of triangles. Even though we don't see any triangles, think about, you have the center A, and those points C and D are on the circle. So what if you drew in a radius AC and you drew in another radius AD? Now do you see two triangles there? This one and then the one adjacent to that right there. Hopefully you can see those, and you've made the invisible visible now. Since those are radii, by our circle definition, those would be the same. So we could put one tick mark on each of those. And then those two triangles, they have AE in common. So that's axiom 4, our reflexive axiom. So we can put a little circle there. So we have the hypotenuse and one leg. And we know those are right triangles based on our given information there. And then we could prove CE is congruent to DE by corresponding parts of congruent triangles are congruent. So let's just go ahead and start making our two-column proof. And anytime you're asked now to do a proof, to prove something, you're doing a two-column proof like this with its statements column and its reasons column. So be writing this out with me, don't just watch. This is how you memorize these rules and things too. Write things down. That helps make it stick better in your memory. So first, we write down our given information. That's always what we do. Circle A and AE is perpendicular to CD. And we could put bars over those as well to describe segment AE and C. You don't have to do that, but we can. And so that's given. That's the reason that we wrote that as the first statement. Then we can say that AC is congruent to AD, and we're doing that because of the circle definition from Lesson 9, and we'll put that in parentheses there. It's from Lesson 9. Some math books, they may say that that's a corollary of the circle definition. That's something that follows from that. But we'll just use the circle definition, because within our circle definition, we say that all those line segments, that they have one point in common called the center, and they're all equal to each other, that you can draw from the center to the edge. Now, we've also drawn in that circle there on segment AE, and so what we're saying there is that AE is congruent to AE, which seems pretty obvious, but we write that down anyway, and that's axiom 4. Because we have to, in order to use the hypotenuse leg, we have to show that the hypotenuse is congruent and legs are congruent, so we have to write those things down. And that axiom 4 is in our lesson 10. And so then we can say triangle ACE is congruent to triangle ADE, and those are congruent by hypotenuse leg. And then CE is therefore congruent to DE by CPCTC. Congruent parts of congruent triangles are congruent. Did you notice how this compares to the perpendicular bisector of a chord theorem, where we said if any segment AB passing through center A is drawn perpendicular to a chord, then it bisects the chord. And the converse is also true. In our diagram of the theorem, we had a radius AB that was drawn in that. And of course, we could have just extended AE out to the radius. It would be the same direction and everything. That's why it doesn't have to be a radius. It just has to start at the center like AE did here. Let's do one more, and this proof, you've been given tangents TG and TH, and then also circle F. Prove that JG is congruent to JH. Now, something to think about here, this F, T, and GH, they look perpendicular, right? But we weren't given that they are. So, in other words, we're not going to use the perpendicular bisector of a chord theorem because we weren't given that those are perpendicular to show that JG and JH are congruent. So, it's better not to assume that it's true, and instead just solve the proof based off the given information and using the side, and side angle side theorems in the proof. Now, the tangent segments theorem, that tells us that TG and TH are congruent. So let's go ahead and put some marks on those. TG and TH are congruent. And you should be thinking already that you're supposed to be using and trying to see triangles in here that you can show that are congruent to each other. Then we could use our circle definition to add radii FG and FH right there. So we'll put 2 tick marks on those to show that those are congruent. And then do you see triangle FGT and FHT? And they both share side FT, so we could put a oval or circle right there to show that they have that in common by axiom 4. So those triangles are congruent by side. Then notice this, look at triangle GFJ right in there. And look at triangle HFJ right in there. We could say that those two are congruent by side angle side, and therefore JG and JH are congruent by CPCTC. So let's go ahead and get started. Make our statements and reasons column. There's our statements column, then our reasons column. If you want to, you can pause the lecture and see if you can figure out the proof on your own, write it down, and then fast forward to the results at the end. So we know the given information is tangents TG and TH, and then circle F. That's given. And just redrawing a little bit here because I'm afraid I'm going to run out of room. And so we have FG is congruent to FH. And so that's our circle definition. That's in lesson 9. Next, we'll say that TG is congruent to TH, and that's our tangent segments, TH for theorem, and that's in a lesson 11. That was one of the ones we said at the beginning of the lesson that we might be using. And then FT is congruent to FT by Axiom 4. And that's in lesson 10. Don't have to do that, but it's a good idea just to reference where that came from. And then triangle FGT is congruent to triangle FHT by side, side, side. Then we could say that angle GFJ is congruent to angle HFJ by CPCTC. So do you see that angle? We didn't really mark it off yet. Angle GFJ, this one right in there, is congruent to HFJ, this one right there. Those are congruent to each other because they're inside those triangles, right? That we just said are congruent. So CPCTC on that. Then those small triangles, they share side FJ, so FJ is congruent to FJ by Axiom 4. Again, it's okay to use the same reason more than once. There's no reason you can't use the same reason more than once. And then triangle GFJ is congruent to triangle HFJ by side angle side, and JG is therefore congruent to JH by CPCTC. So we've proven that. There's also no reason you can't use two triangle congruency theorems in the same proof either. We had to use two different ones because there was two different triangles we had to work with there. That's just what you have to do sometimes, is use more than one triangle congruency theorem in a proof. Okay, well that's all for lesson 60.